There are moments in science that rewrite history, not with a bang, but with a whisper. Picture this: deep in the quiet halls of an observatory, a team of scientists stares at their screens as a ripple passes through their detectors. It's not a sound, not a flash of light, but something far stranger, a vibration in the fabric of space itself. On that day, the universe spoke in a language we had never heard before: gravitational waves. These were the echoes of a cataclysm that happened more than 1 billion years ago, when two black holes, locked in a deadly dance, finally collided. The energy released was unimaginable, enough to shake the cosmos. And yet, here on Earth, it arrived as nothing more than a faint tremor, a silent scream from the depths of space. What makes this discovery so extraordinary isn't just the violence of that collision, but the paradox it reveals. How can something so powerful, so destructive, leave no trace in the air, no sound for our ears to hear? Gravitational waves don't travel like sound or light. They move through the very structure of reality, bending space and time as they pass. They're the universe's way of whispering its secrets directly to us, bypassing everything we thought we knew about how to listen. For centuries, we've relied on telescopes to see the cosmos. But now, we've unlocked a new sense, one that lets us feel the universe's hidden rhythms. This is the mystery we're about to unravel. A collision so colossal it sent shockwaves across the cosmos, yet landed on our detectors in utter silence. What does it mean to hear the universe when there's no sound at all? How do these invisible waves reshape our understanding of black holes, time, and even the birth of the cosmos itself? The answers are as thrilling as they are profound, and they're waiting just ahead. So let's dive into the story of gravitational waves, where the universe's loudest collisions are also its quietest whispers, and where every ripple carries a secret older than stars. Albert Einstein first dreamed of gravitational waves in 1916 as a strange ripple hidden within the equations of his general theory of relativity. He imagined space not as an empty stage, but as a stretchy fabric, one that could bend, twist, and even shudder under the weight of massive objects like stars and black holes. But here's the twist: Einstein himself doubted we'd ever detect these waves. The distortions were too tiny, too subtle, buried in the noise of a restless universe. For decades, the hunt for gravitational waves seemed like chasing ghosts until a handful of stubborn scientists refused to give up their tool of choice. A machine so precise it could measure changes smaller than 1/10,000th the width of a proton. Welcome to LIGO, the Laser Interferometer Gravitational Wave Observatory, a pair of colossal L-shaped detectors stretching 2.5 miles through the deserts of Washington and Louisiana. Inside these tunnels, lasers bounce between mirrors, waiting for the faintest tremor in space-time. Year after year, the detectors listened to silence until September 14, 2015. That's when the universe finally spoke. The signal lasted just 0.2 of a second, a blip, a flicker, but hidden in that flicker was the story of two black holes, each 30 times heavier than our sun, spiraling toward each other at half the speed of light. When they collided, they unleashed more energy in an instant than all the stars in the observable universe combined. And yet, by the time those ripples reached Earth, they'd faded to a whisper, stretching and squeezing LIGO mirrors by less than the width of an atom. What's astonishing isn't just the detection, but what it revealed. Gravitational waves don't behave like light or sound. They're not blocked by dust or dimmed by distance. They slip through planets, stars, even entire galaxies untouched. That means they carry stories light can't tell, like the final moments of invisible black holes or the birth cries of the universe itself. Before LIGO, astronomy was like watching a silent movie. Now, we've been handed the soundtrack. The collision that started it all was a cosmic paradox, an event so violent it warped the fabric of reality, yet so delicate we needed the most sensitive machine ever built just to feel its echo. And that's the magic of gravitational waves. They're the universe's way of shouting in a language we had to learn to hear. Imagine tossing a pebble into a still pond. The moment it hits the water, ripples spread outward in perfect circles, growing fainter as they travel. Gravitational waves move through the cosmos in much the same way, except instead of water, they ripple through the very fabric of space-time itself. These waves are born from the most violent events in the universe, colliding black holes, merging neutron stars, even the echoes of the Big Bang. When massive objects like these accelerate or collide, they don't just move through space, they warp it, sending distortions racing outward at the speed of light. But here's what makes them so strange. Unlike sound waves, which need air to travel, or light, which can be blocked by dust, gravitational waves pass through everything. Planets, stars, even you and me, they ripple right through us, completely undetectable to our senses. That's why we call them waves, even though we can't hear or see them. They're not a vibration in matter, but in the invisible framework of reality. Think of it like a silent earthquake shaking the foundations of the universe, a tremor so subtle, it took us a century to build a machine sensitive enough to catch it. This cosmic whisper carries information nothing else can. Light gets absorbed, scattered, or distorted as it travels across the universe, but gravitational waves arrive pristine, unchanged from the moment they were born. They're like cosmic telegrams, delivering unfiltered news from events billions of years ago. When two black holes spiral into each other, their gravitational waves tell us not just where they happened, but how massive they were, how fast they were spinning, even the direction of their final, fatal dance. It's as if the universe left us a voicemail, one that took 1 billion years to reach our detectors. And that's the real magic of these waves. They're not just a new way to observe the cosmos, they're a whole new sense, letting us perceive things we could never see with telescopes. Before gravitational waves, black holes were silent phantoms, invisible against the darkness of space. Now we can hear them collide. Neutron stars, the dense remnants of dead suns, reveal their secrets in the ripples they create when they merge. Even the first chaotic moments after the Big Bang might be encoded in gravitational waves still washing over us today. So how do we catch something so elusive? The answer lies in a dance of lasers and mirrors, patience and precision, and a machine so sensitive it can detect a distortion smaller than a single atom. The story of how we learn to listen to space-time isn't just about science. It's about redefining what it means to explore the universe. The universe has a soundtrack, but it's one our ears were never built to hear. Gravitational waves don't create sound in the way we understand it. There's no air in space to vibrate, no medium to carry a noise. Instead, these waves are distortions in space-time itself, stretching and squeezing the cosmos like an invisible accordion. So why do scientists talk about hearing them? The answer lies in a brilliant act of translation, turning the silent tremors of the universe into something our brains can process. Think of it like a radio telescope picking up invisible signals from distant stars. Our ears can't detect radio waves, but by converting them into sound, we make the cosmos audible. Gravitational wave observatories do something similar. When LIGO detects a ripple, scientists shift its frequency, stretching out those faint cosmic vibrations until they fall within the range of human hearing. Suddenly, a collision of black holes becomes a soft chirp, a rising tone that lasts barely a heartbeat. Neutron stars merging sound like a quick, metallic thud. These aren't real sounds, of course, they're sonic fingerprints, a way for us to experience events that would otherwise be utterly silent. This translation reveals something profound about how we explore the universe. Just as dark matter betrays its presence only by tugging on galaxies, or black holes cast shadows against bright gas, gravitational waves are another hidden layer of reality we've learned to decode. They remind us that the cosmos is full of phenomena we can't see, touch, or hear directly, but with the right tools, we can glimpse their secrets. The technology behind this cosmic eavesdropping is nothing short of miraculous. LIGO lasers measure shifts smaller than a single proton, while supercomputers sift through mountains of data to separate genuine signals from earthly noise, passing trucks, distant earthquakes, even the rumble of ocean waves. It's like trying to hear a pin drop in a hurricane, yet when a gravitational wave passes through, the pattern is unmistakable, a ripple in the data that matches Einstein's century-old equations with eerie precision. What's even more astonishing is how these silent signals change our relationship with the universe. For the first time, we're not just observers, we're listeners, tuning in to a cosmic symphony played on the strings of space-time itself. Every chirp, every thud is a message from the depths of time, carrying stories of collisions that happened before Earth even formed. And just as a musician learns to hear the emotion behind the notes, scientists are beginning to understand the language of these waves, a silent song that's rewriting the story of the cosmos. Buried beneath the quiet landscapes of Washington and Louisiana lies one of humanity's most extraordinary machines, LIGO, a silent sentinel tuned to the faintest murmurs of the cosmos. Picture two colossal L-shaped tunnels, each stretching 2.5 miles into the distance, their walls so precisely aligned that even a passing cloud or a distant earthquake could disrupt their delicate balance. Inside these tunnels, lasers bounce between mirrors, traveling back and forth like metronomes keeping perfect time. The goal, to catch the moment when a gravitational wave, a ripple in space-time itself, passes through Earth, stretching one arm of the detector while squeezing the other. The distortion it's looking for is almost unimaginably small, a shift in distance smaller than 1/10,000th the width of a proton. To put that in perspective, it's like measuring the distance to the nearest star and detecting a change no wider than a human hair. LIGO isn't just a feat of engineering, it's a triumph of collaboration. Scientists from over 20 countries pooled their expertise to build this cosmic ear, with sister observatories like Virgo in Italy and Kagra in Japan joining the hunt. Together, they form a global network, triangulating signals to pinpoint the origin of gravitational waves across the universe. Why does this matter? Because a single detector might mistake a passing truck or a minor earthquake for a cosmic event. But when multiple observatories thousands of miles apart detect the same ripple, the odds of a false alarm drop to nearly zero. It's like having multiple witnesses to a crime, each one confirming the other's story. The real magic, though, lies in what these detectors have heard. On September 14, 2015, LIGO caught its first unambiguous signal, a fleeting chirp lasting just 0.2 of a second. Hidden in that blip was the death spiral of two black holes, each around 30 times the mass of our Sun, orbiting each other hundreds of times per second before merging in a catastrophic collision. The energy released was so immense that, for a fraction of a second, it outshone every star in the observable universe combined. Yet by the time those ripples reached Earth, they'd faded into near nothingness, warping LIGO mirrors by less than the width of an atom. This detection didn't just confirm Einstein's century-old prediction, it opened an entirely new window on the universe. Before LIGO, black holes were ghostly shadows, invisible against the darkness of space unless they were devouring nearby stars. Now we can hear them collide. Neutron stars, the ultra-dense remnants of dead suns, reveal their secrets in the ripples they create when they spiral together. Even the violent birth of the universe might leave traces in primordial gravitational waves, whispers from the first moments after the Big Bang. What makes LIGO so revolutionary isn't just its sensitivity, but its ability to capture events no telescope could ever see. Light can be blocked by dust or distorted by gravity, but gravitational waves slip through everything untouched. They're the universe's unfiltered broadcast, carrying stories from the darkest, most distant corners of space. And with every new detection, we're not just observing the cosmos, we're learning to listen to it. On September 14, 2015, the universe delivered a message humanity had been waiting a century to receive. At 5:51 in the morning, Eastern Time, gravitational waves from an event dubbed GW150914 washed over Earth, ripples from a collision so cataclysmic it defies imagination. Over 1.3 billion years earlier, in a distant corner of the cosmos, two black holes, each roughly 30 times the mass of our Sun, had been locked in a spiraling death dance. Orbiting each other hundreds of times per second, moving at half the speed of light, they finally merged in a violent embrace. In that instant, 3 times the mass of our Sun vanished not into light or heat, but into pure gravitational energy, warping the fabric of spacetime itself. The resulting shockwave raced outward at the speed of light, carrying echoes of the collision across galaxies until it reached a tiny, insignificant planet called Earth. What made this detection so extraordinary wasn't just the scale of the event. It was how loud it was in gravitational wave terms. Scientists measure these signals in units called strain, which captures how much spacetime stretches and squeezes as a wave passes. GW150914 produced a strain so strong that LIGO detectors, despite being separated by nearly 2,000 miles, both picked it up within milliseconds of each other. To put that in perspective, the distortion it created was like stretching the entire Milky Way galaxy by the width of a single atom, a change so minuscule, yet so unmistakable against the quiet hum of the universe. But here's the paradox. This was a cosmic explosion with no flash, no sound, no debris. The black holes left no trace except the ripples in space-time they created. That's because black holes are the universe's ultimate shadows, regions where gravity is so strong that not even light can escape. Without gravitational waves, their collisions would be invisible, hidden behind the curtain of absolute darkness. Yet the energy released was staggering. For a fraction of a second, the merger outshone every star in the observable universe, combined not in light, but in raw gravitational power. This event didn't just confirm Einstein's prediction, it shattered expectations. Before GW150914, many scientists doubted black holes of this size could pair up so closely. The discovery revealed a hidden population of binary black holes lurking in the cosmos, waiting to collide. It also proved gravitational waves could carry detailed information across billions of years, untouched by dust, gas, or the chaos of space. Unlike light, which dims and scatters, these waves arrived pristine, a perfect snapshot of a moment older than multicellular life on Earth. Perhaps most astonishing was how quickly humanity went from skepticism to certainty. Within months, the LIGO team had analyzed the signal down to the millisecond, matching it perfectly to supercomputer simulations of merging black holes. The odds of a false alarm, less than 1 in 200,000. This wasn't just a detection, it was the birth of an entirely new way to explore the universe. Suddenly, we had proof that space-time could tremble like the surface of a drum, and that the loudest beats came from events we'd never seen, only heard. And this was just the beginning, the first note in a symphony written in the language of gravity itself. Black holes are the universe's most enigmatic architects of chaos, objects so dense that not even light can escape their grip. Yet for all their destructive reputation, they're not the cosmic vacuum cleaners pop culture often portrays. Imagine a star 10 times more massive than our sun collapsing in on itself, crushing down to a point smaller than a city. That's a black hole, a singularity wrapped in an invisible boundary called the event horizon, where gravity's pull becomes irreversible. But here's what's fascinating: black holes aren't just passive traps. They're dynamic, messy, and surprisingly social. When two black holes orbit each other, their gravitational pull doesn't just bend space, it churns it, sending out ripples like a paddle dragging through water. These ripples are gravitational waves, and they carry the fingerprints of the black holes that created them. Picture two black holes spiraling closer, their immense gravity distorting space-time like dancers twisting a sheet between them. As they accelerate, reaching speeds nearing half the speed of light, the waves grow stronger, screaming across the cosmos long before the final collision. When they finally merge, the resulting black hole doesn't settle quietly. It rings like a struck bell, vibrating space-time until it smooths into a new, larger singularity. That ringing is what LIGO detected: a fleeting chirp encoding the masses, spins, and even the direction of the black hole's final orbit. What defies intuition is how gentle these titans can seem from afar. A black hole's gravity near its event horizon is terrifying, capable of shredding stars into spaghetti-like streams. But from a distance, its pull is no stronger than a star of the same mass. If our sun were suddenly replaced by a black hole of equal mass, Earth's orbit wouldn't change. We'd just freeze in the dark. This nuance is key. Black holes warp space-time not because they're hungry, but because they're unimaginably compact. A teaspoon of black hole material would weigh billions of tons, bending the fabric of reality around it like a bowling ball on a trampoline. The collisions themselves are where physics reaches its limits. When two black holes merge, they release energy equivalent to converting several suns into pure gravitational waves. For a fraction of a second, the event outshines entire galaxies, not in light, but in ripples that stretch and squeeze the universe itself. Yet the aftermath is eerily simple. A single, larger black hole, its surface area paradoxically greater than the sum of its parents. This isn't destruction, it's transformation, a cosmic rebranding written in the language of warped space-time. What remains a mystery is what actually happens during that collision. Behind the event horizon, our equations break down. Time and space swap roles, densities become infinite, and the laws of physics as we know them cease to apply. Some theories suggest the black hole's singularities might merge into a bridge, a wormhole, or that information swallowed by the black holes gets scrambled and ejected in the gravitational waves. Others propose that the event horizon itself trembles, shedding hair in the form of quantum particles. What we do know is this: every merger is a laboratory for testing Einstein's theory under extremes he never imagined. And with each detection, we're decoding the universe's most violent, silent conversations. Two black holes circling each other is like watching the universe's most dangerous ballet, a dance where the performers are invisible. The stage is space-time itself, and the finale is a collision of unimaginable force. As they spiral closer, their gravity distorts everything around them, stretching light into bizarre arcs and slowing time itself. Imagine two colossal weights spinning on a cosmic trampoline, each orbit tightening faster and faster until they're whipping around at nearly half the speed of light. The energy radiating outward isn't light or heat. It's pure gravitational power warping the fabric of reality like ripples on a pond. Then comes the moment of impact. In less time than it takes to blink, the two singularities, each a point of infinite density, merge into one. The forces at play here are beyond comprehension. For an instant, the new black hole isn't smooth and round but a roiling, misshapen mess, vibrating wildly as it settles into its new form. These vibrations aren't sound, they're space-time itself ringing like a struck bell, sending gravitational waves racing outward at light speed. The energy released is staggering, the equivalent of several suns converted entirely into ripples in the cosmos. It's the universe's way of shouting without making a sound. What's astonishing isn't just the violence of the collision, but what it tells us. The shape of those gravitational waves carries hidden details like cosmic fingerprints. Scientists can decode them to learn the black hole's masses, how fast they were spinning, even the angle of their final death spiral. This isn't just a crash, it's a laboratory for testing Einstein's theories under conditions no earthly experiment could replicate. The merger proves space-time isn't just a static backdrop. It's dynamic, elastic, capable of trembling under the weight of such titanic events. And then silence. The new black hole, now heavier than its parents, sits quietly in the void, its event horizon smooth and featureless. All traces of the collision are gone except for those gravitational waves, still racing outward, carrying the story of that cataclysm to anyone listening. This is the paradox of black hole mergers. The most violent events in the cosmos leave no visible scars, no debris, no afterglow. Their entire history is written in distortions of space itself, a language we've only just begun to understand. What secrets do these collisions hold? They might reveal how black holes grow so massive, or whether exotic objects like wormholes could exist. Some theories suggest the echoes of these mergers could even hint at hidden dimensions, or the quantum nature of gravity itself. Every chirp LIGO detects is a piece of a puzzle, one that stretches back to the birth of the universe and forward to the far future, when the last black holes will evaporate into nothingness. The dance of merging black holes isn't just a spectacle, it's a key to unlocking the deepest mysteries of space, time, and the very fabric of reality. Gravitational waves are more than just cosmic ripples, they're encrypted messages from the universe, carrying secrets about the events that created them. Think of each wave like a fingerprint, its unique shape revealing details about the objects that left it behind. When two black holes collide, the resulting gravitational waves encode their masses, how fast they were spinning, even how far away they were. It's as if the universe handed scientists a detective's toolkit, letting them reconstruct cosmic crime scenes from nothing but tremors in space-time. Decoding these signals is a feat of precision that borders on the miraculous. Take LIGO first detection, the faint chirp lasting just 0.2 of a second. Hidden in that blip was a wealth of information. By comparing the wave's shape to supercomputer simulations, physicists could tell the black holes were roughly 30 times the mass of our Sun, spinning at dizzying speeds before merging. They even calculated how much energy vanished into gravitational waves, the equivalent of 3 suns vaporized into pure space-time vibrations. All this from a signal so weak it moved LIGO mirrors by less than the width of an atom. The real magic lies in how gravitational waves complement traditional astronomy. Light can show us what cosmic objects look like, but these waves tell us how they move. Imagine trying to understand a car crash by only studying the debris versus hearing the screech of brakes, the impact, the crumple of metal. Gravitational waves provide that soundtrack. When neutron stars collided in 2017, telescopes saw the aftermath, a glowing kilonova, while LIGO captured the moment of collision itself, revealing details about their structure no light-based observation could. What makes these discoveries so transformative is their reach. Gravitational waves travel unimpeded. carrying pristine information from events hidden behind dust clouds or buried in the cosmic dark ages. They've already exposed surprises like black holes pairing up in ways theorists didn't predict, and they might soon detect echoes from the Big Bang itself. Every new ripple adds a piece to the puzzle, rewriting textbooks one whisper at a time. This isn't just about cataloging cosmic crashes. It's about learning to read the universe's hidden language, a code written not in light or sound, but in the very fabric of reality. And with each detection, we're deciphering another line in the cosmos' grand autobiography. Einstein's theory of general relativity was a masterpiece of imagination, a radical rethinking of gravity not as a force, but as the curvature of space-time itself. Yet for all its brilliance, one of its most astonishing predictions remained unproven for a century: the existence of gravitational waves. When LIGO finally detected those elusive ripples in 2015, it wasn't just a scientific milestone, it was the culmination of a quest that tested the limits of human ingenuity. The story begins in 1916, when Einstein first scribbled equations suggesting that accelerating massive objects should send waves through space-time. But even he wavered, at one point publishing a paper claiming these waves couldn't exist, only to reverse himself later. The math was clear, but the physics seemed impossible. How could anyone detect distortions smaller than a proton across interstellar distances? For decades, the hunt was dismissed as a fool's errand, until a stubborn few refused to let the dream die. Enter Joseph Weber, a physicist who built the first gravitational wave detector in the 1960s using aluminum bars designed to ring like bells if a wave passed through. His claims of detection were met with skepticism, but his work inspired a new generation. By the 1970s, visionaries like Rainer Weiss and Kip Thorne were sketching designs for laser interferometers, machines so precise they could measure the faintest tremors in space-time. It would take 40 more years of trial, error, and technological leaps to turn those sketches into LIGO. The detection of GW 150914 wasn't just a victory for Einstein, it was a triumph of persistence. The signal matched his predictions with uncanny precision, confirming that space-time really does ripple like the surface of a pond. But the real surprise was how loud the universe turned out to be. Before LIGO, theorists assumed black hole collisions would be rare. Instead, detections now roll in regularly, sometimes monthly, revealing a cosmos far more violent and dynamic than anyone imagined. This validation didn't just cement Einstein's legacy, it opened new paradoxes. Why are there so many massive black hole pairs? How do they form so close together? Some mergers defy expectations, like the impossible black hole weighing 85 solar masses, a size theory says shouldn't exist. Each discovery peels back another layer, proving that even a century-old theory still holds mysteries waiting to be unraveled. Gravitational waves have done more than confirm relativity. They've given us a tool to probe the universe's darkest corners. They're rewriting the rules of black holes, exposing gaps in our understanding of neutron stars, and may soon reveal secrets from the first moments after the Big Bang. Einstein's equations were the map, but now, thanks to those who dared to chase his ghostly waves, we're finally learning to navigate the terrain. Black holes are the universe's ultimate ghosts, colliding with unimaginable force, yet leaving no visible trace. When two black holes spiral into each other, their merger is a spectacle of pure gravity, warping space-time so violently that the energy released could outshine all the stars in the sky. But here's the catch: there's no flash of light, no burst of X-rays, not even a flicker of radio waves. These events are utterly dark, earning them the nickname silent collisions. Why? Because black holes are cosmic vacuums, their gravity so strong that anything crossing their event horizon, including light, vanishes forever. no material swirls around them to heat up and glow. No debris is left to scatter radiation, just two invisible giants merging in perfect silence, their story told only through the ripples they send shaking through the fabric of reality. Now compare that to a neutron star collision, a cosmic fireworks show. When these ultra-dense stellar remnants collide, they don't just send out gravitational waves. They also light up the sky in a blaze of gamma rays, X-rays, and even visible light, creating what astronomers call a kilonova. The difference comes down to what's on the surface. Neutron stars aren't black holes, they're made of matter, cramming a sun's worth of material into a city-sized sphere. When they smash together, that matter gets shredded, flung outward in a superheated spray that glows with the energy of nuclear reactions. These collisions forge heavy elements like gold and platinum, scattering them across space in a glittering aftermath telescopes can spot from billions of light years away. Studying silent collisions is like investigating a crime scene with no fingerprints, no witnesses, and no murder weapon, just a faint tremor in the floor. Traditional astronomy relies on light, but black hole mergers defy that entirely. Without gravitational waves, we'd have no way to know these events were happening at all. That's why detectors like LIGO and Virgo are revolutionary. They're not just adding to our toolkit, they're revealing an entire hidden layer of the universe. But silence isn't just a challenge, it's a clue. The absence of light tells us something profound about black holes. They're clean. No gas, no dust, no messy stellar material to complicate the signal. That purity lets gravitational waves carry undistorted information across billions of years, offering scientists a pristine window into the physics of extreme gravity. To bridge the gap, researchers are now pairing gravitational wave data with other tools, like neutrino detectors or even searches for hypothetical dark matter signals. It's a cosmic detective story where every missing piece of evidence is itself a revelation, the next frontier catching a merger that isn't entirely silent. Some theories suggest rare black hole collisions might occur in gas-rich environments where swirling material could glow just before being swallowed. Others hunt for orphaned gamma-ray bursts, mysterious flashes that might be the distant echoes of black holes feeding. With upgrades to LIGO and new observatories like the space-based LISA, we're on the verge of hearing and maybe even seeing the universe's quietest catastrophes in ways Einstein never dreamed possible. For centuries, astronomers relied on a single sense sight to explore the cosmos. But in 2017, something extraordinary happened. We witnessed a cosmic event with both our eyes and our ears for the first time. This was the dawn of multi-messenger astronomy, a revolutionary approach that combines gravitational waves with traditional observations like light, X-rays, and even ghostly neutrinos. The event, a pair of neutron stars colliding 130 million light-years away, sending ripples through space-time that reached Earth on August 17th. But unlike silent black hole mergers, this crash came with a fireworks show. A burst of gamma rays detected just 2 seconds after LIGO gravitational wave alert. Telescopes around the world swiveled to catch the aftermath, revealing a glowing kilonova that faded over days, its light laced with newly forged gold and platinum. Here's why this was a game-changer. Gravitational waves told us how the neutron stars moved their masses, spins, and final moments before merging. Light revealed what they were made of, the heavy elements spewed into space, solving a decades-old mystery about where gold in the universe comes from. Together, these messengers painted a complete picture, like hearing a symphony while watching the orchestra play. It confirmed that neutron star collisions are cosmic forges, producing rare elements in their violent aftermath. But the real surprise was how perfectly the signals matched. Einstein predicted gravitational waves would travel at light speed, and here was proof down to the second. Multi-messenger astronomy doesn't just add layers to our understanding, it uncovers connections we'd never see otherwise. Take black holes with companion stars. While their mergers are silent, the swirling gas around them might glow beforehand, giving telescopes a heads up. Or consider supernova. Gravitational waves could reveal the moment a star's core collapses, while light shows the explosion's aftermath. Even neutrinos, elusive particles that zip through Earth undetected, might carry clues when paired with gravitational waves. Each messenger fills in gaps the others can't, like detectives comparing notes to solve a cosmic crime. The future of this field is bursting with possibility. Upcoming observatories like the space-based LISA will detect lower frequency waves, capturing the slow dance of supermassive black holes years before they collide. Meanwhile, telescopes like the Vera Rubin Observatory will scan the sky nightly, ready to spot the faintest glimmers tied to gravitational wave events. And with neutrino detectors growing more sensitive, we might soon catch all three signals at once: waves, light, and particles, from a single cataclysm. This isn't just about new tools, it's about rewriting how we explore the universe. We're no longer passive observers, but active listeners, decoding a symphony where each instrument reveals a different truth. And as the next generation of detectors comes online, one thing is certain: the cosmos still has surprises waiting in the dark. Black holes may be the loudest players in the gravitational wave symphony, but they're far from the only instruments. Across the cosmos, other violent and mysterious events are bending space-time in their own unique ways, each with a signature as distinct as a fingerprint. Take supernova, the explosive deaths of massive stars. When a star's core collapses, it doesn't just vanish, it rebounds in a shockwave that sends space-time shuddering. Unlike the clean chirp of merging black holes, a supernova's gravitational waves would be chaotic, a cacophony of spikes and rumbles reflecting the star's asymmetric collapse. Some models suggest these waves could even carry hints about what happens deep inside a dying star, regions no telescope can ever peer into directly. Then there are pulsars spinning neutron stars that act like cosmic lighthouses. If one of these ultra-dense objects develops a mountain just millimeters high on its surface, its rapid rotation would send continuous gravitational waves rippling outward. These wouldn't be the sharp bursts of collisions, but a steady hum, like a tuning fork vibrating across the universe. The challenge: detecting this whisper-thin signal requires years of patient listening, separating it from the noise of passing trucks and ocean waves that can jiggle our detectors here on Earth. But perhaps the most elusive prize of all is the gravitational echo of the Big Bang itself. In the first fraction of a second after the universe began, quantum fluctuations in the newborn cosmos may have stretched into primordial gravitational waves, a fossil imprint of creation itself. These waves would be immeasurably faint now, stretched to wavelengths longer than the solar system by 14 billion years of cosmic expansion. Yet if we could catch them, they'd offer a glimpse past the curtain of the cosmic microwave background, into realms no light-based observation can reach. What else might be out there waiting to surprise us? Exotic objects like cosmic strings, hypothetical defects in space-time from the early universe, could snap and send sharp gravitational wave bursts. Colliding wormholes might produce bizarre, mirrored signals unlike anything in our models. Some theorists even speculate about gravitational wave background, a sea of overlapping ripples from countless unseen events, creating a faint static in the fabric of reality. Catching these whispers demands technology that pushes the boundaries of the possible. Next-generation detectors like the space-based LISA, a trio of satellites forming a million-mile-wide gravitational wave antenna will hunt for low-frequency signals impossible to detect on Earth. Cryogenic sensors cooled near absolute zero could reduce quantum noise, while atomic interferometers may one day sense space-time ripples using clouds of ultra-cold atoms. Each advance isn't just about better hardware, it's about rewiring how we perceive the universe, trading telescopes for vibrational ears attuned to the subtle tremors of existence. This is the new frontier, a cosmos where every cataclysm leaves an imprint in space-time, where the universe's darkest corners are no longer silent. As our detectors grow more sensitive, we're not just adding to astronomy, we're reinventing it, one vibration at a time. The hunt for gravitational waves is about to leap into a new era, one where our cosmic ears grow so sensitive we could catch whispers from the dawn of time itself. Right now, Earth-based detectors like LIGO are limited by the planet's own restlessness. Earthquakes, ocean waves, even the rumble of distant traffic create noise that drowns out the faintest ripples. But imagine a detector floating in the pristine silence of space, free from Earth's vibrations, with arms so long they stretch millions of miles. That's LISA, the Laser Interferometer Space Antenna, a revolutionary observatory set to launch in the 2030s. Instead of tunnels, it'll use 3 spacecraft flying in perfect formation, firing lasers between them to measure distortions 100 times smaller than LIGO can detect. With this kind of precision, LISA won't just hear black hole mergers, it'll catch their slow-motion courtship, tracking pairs for years before they collide. Even more ambitious is the Einstein telescope, a next-generation underground detector shaped like a giant triangle with arms 10 times longer than LIGO. Buried deep beneath Europe to shield it from surface noise, it'll be so sensitive it could pick up gravitational waves from neutron stars wobbling like unbalanced washing machines, or even the faint echoes of the universe's first black holes, born in the chaos after the Big Bang. These projects aren't just upgrades, they're quantum leaps, promising to reveal entire populations of cosmic objects we've only theorized about. Supermassive black holes orbiting each other in distant galaxies, primordial ripples from cosmic inflation, even exotic relics like cosmic strings. If it warps space-time, these detectors will find it. What's striking is how these efforts span the globe. LISA is a European Space Agency mission with NASA, a collaboration, while the Einstein telescope unites researchers from 10 countries. Japan's Kagra detector, nestled in a mine to stay cryogenically cool, complements India's planned LIGO India, creating a worldwide network that can pinpoint gravitational wave sources with surgical precision. This isn't just science, it's diplomacy, with nations pooling expertise to build machines no single country could tackle alone. But beyond the technology lies a deeper question. What does it mean to hear the universe's birth cries? Gravitational waves from the cosmic dawn would carry untouched information from a time before stars, before atoms, even before light could travel freely. They'd let us test theories of quantum gravity, probe hidden dimensions, and maybe even glimpse what came before the Big Bang. It's humbling to realize that these waves, forged in violence and silence, might hold the keys to existence itself, and we're just now learning to listen. For centuries, humans gazed at the night sky and saw a silent, unchanging tapestry, stars fixed in their constellations, planets moving in predictable rhythms, a cosmos frozen in perfect stillness. But gravitational waves have shattered that illusion, revealing a universe alive with motion, a place where space-time itself thrums with energy. Those faint ripples we detect aren't just scientific curiosities, they're proof that the cosmos is more like a vast, whispering ocean than a static painting. Every collision, every cataclysm sends tremors through the fabric of reality, a symphony written in distortions too subtle for our ancestors to imagine. It's poetic, really, how closely this mirrors the ancient idea of the music of the spheres, the belief that celestial bodies moved in harmonies only the universe could hear. Pythagoras dreamed of it, Kepler scribbled equations for it, poets and mystics wove it into their visions of the divine. Now, science has given us the tools to hear that music for real, not as metaphor but as mathematics. The difference, instead of perfect celestial chords, we're listening to the chaotic crescendo of black holes colliding, neutron stars spinning, and stars dying in explosions that warp space-time itself. This new reality raises an exhilarating question. If we're already hearing these cosmic drumbeats, what else might be out there just beyond our current reach? Could there be gravitational murmurs from the birth of the first stars, or the faint hum of dark matter interactions we've yet to understand? Some theories even suggest space-time might carry echoes from before the Big Bang, ghostly vibrations from universes that existed before our own. Every improvement in our detectors peels back another layer of cosmic noise, like tuning a radio to frequencies we never knew existed. Yet for all we've discovered, the unknowns still loom large. Why do some black holes pair up so easily, while others seem to roam alone? What secrets do neutron stars hide beneath their crushing gravity? And could gravitational waves ever reveal the presence of something truly bizarre, wormholes, extra dimensions, or cracks in the laws of physics? The more we listen, the more the universe surprises us, proving that even Einstein's towering theories might only be the first movement in a much grander composition. The beauty of this moment is that we're not just observers anymore, we're participants in a conversation with the cosmos. Every chirp, every ripple is a clue waiting to be deciphered, a whisper from the dark urging us to lean in closer. And as our technology grows sharper, one thing is certain: the universe has only just begun to speak. Some of the universe's most violent collisions happen in perfect darkness. No flash of light, no burst of radiation, just the faintest tremor in the fabric of space-time. Black hole mergers are the ultimate ghosts of the cosmos, vanishing without a trace the moment they collide. While neutron star crashes paint the sky with glittering kilonovas, these silent events leave astronomers staring into an empty void, grasping at echoes. The mystery isn't just why they're invisible, it's what their silence reveals about the hidden corners of the universe. Take the environment where these mergers occur. Most black hole pairs are thought to form in dense stellar nurseries, where gas and dust should theoretically glow as they spiral into the abyss. Yet LIGO detections show no such fireworks. One explanation: these black holes might have been born in isolation, far from the chaotic stellar factories that light up their surroundings. Imagine two drifters meeting in a desert, no witnesses, no trail, just the quiet aftermath of their encounter. Another theory suggests the gas around them could be so sparse that any light emitted is too faint to reach us across cosmic distances. It's like trying to spot a match flickering on the other side of a foggy mountain range. Then there's the nature of the objects themselves. Black holes aren't just dark, they're cosmic vacuum cleaners, swallowing everything that ventures too close, including the material that might otherwise glow. Unlike neutron stars, which rip each other apart in a shower of sparkling debris, black holes merge cleanly, their event horizons sewing shut behind them like a zipper closing on reality. No debris means no light, just a perfectly dark handshake between two gravitational titans. But here's where it gets stranger. Some models predict that under the right conditions, even black hole mergers could produce faint electromagnetic signals if they're surrounded by disks of gas or orbiting stars that get disrupted in the chaos. The hunt for these elusive counterparts is like searching for a single firefly in a pitch-black stadium. teams of astronomers now scramble with every LIGO alert, scanning the skies for any flicker that might betray a silent collision. So far, the scoreboard remains empty, deepening the enigma. What makes these dark mergers so valuable is precisely what makes them so frustrating: their purity. Without light pollution to complicate the signal, their gravitational waves arrive pristine, carrying uncontaminated data about the physics of extreme gravity. They're nature's cleanest experiments, testing Einstein's theories in ways no lab ever could. And with upgrades to detectors like LIGO and Virgo, scientists are inching closer to catching even fainter whispers, perhaps from black holes merging in the earliest epochs of the universe before stars had lit up the cosmos. The next frontier, listening for the unexpected. Some theorists speculate that a subset of these silent mergers might not involve black holes at all, but exotic objects like boson stars, hypothetical clumps of dark matter particles, or even primordial black holes forged in the Big Bang's first seconds. Others wonder if some collisions occur in entirely dark galaxies, where no stars exist to illuminate the event. Every null result, every silent detection, forces us to rethink what we know about how black holes form, pair up, and vanish into the night. One thing's certain: without gravitational waves, these cosmic specters would remain forever hidden. Their silence isn't a barrier, it's a clue written in the language of warped space-time. And as our detectors grow more sensitive, we're not just solving a mystery, we're learning to read the universe's darkest diary. Simulating the most violent collisions in the universe isn't just about running equations, it's about bending the laws of physics inside a supercomputer until space-time itself unravels on screen. Picture a black hole binary, two invisible giants spiraling toward oblivion. Scientists can't see them directly, so they recreate them digitally, feeding Einstein's equations into machines powerful enough to chew through billions of calculations per second. The result: stunning visualizations where space-time warps like taffy, light bends into surreal arcs, and the collision's shockwaves ripple outward in hypnotic patterns. These aren't artists' impressions, they're mathematical prophecies, precise enough to match the real gravitational waves LIGO detects down to the millisecond. The process starts with a paradox. How do you simulate objects where gravity is so strong, time itself slows to a crawl? The answer lies in adaptive mesh refinement, a computational sleight of hand where the simulation zooms in on the collision with absurd precision, allocating more processing power to the chaotic heart of the merger while simplifying quieter regions. It's like using a microscope that adjusts its lens in real time, focusing only where the action is hottest. Even then, the calculations are so intense that a single simulation can take months, burning through supercomputer time like rocket fuel. What emerges from these digital crucibles is more than just eye candy. The simulations reveal hidden details, like how merging black holes kick each other, launching the final merged black hole at speeds over 1,000,000 miles per hour. They show how neutron star collisions fling out jets of material bright enough to outshine galaxies, or how the event horizon of a colliding black hole stretches into a dumbbell shape before snapping back like a rubber band. These virtual experiments let scientists play cosmic detective, comparing their models to LIGO real-world data to tease out properties like the black hole's spins or the neutron star's internal composition. But the real challenge lies in the unknowns. Simulations rely on our current understanding of physics, yet near a black hole's singularity, even Einstein's equations break down. Some teams are now grafting quantum corrections onto their models, while others probe exotic scenarios like collisions involving wormholes or higher dimensions. Every mismatch between simulation and observation isn't a failure, it's a clue hinting at gaps in our knowledge. When LIGO detected a black hole merger with unexpected ringing in 2019, it was simulations that helped theorists realize they might be seeing evidence of a black hole with tidal deformations, a possibility Einstein never considered. Behind these cosmic recreations are human stories, teams of coders, physicists, and visual artists translating raw numbers into something tangible. Take the group at Caltech that turned a black hole merger into an IMAX film, or the graduate student who spotted a glitch in her simulation that led to a breakthrough in how neutron stars crumble under pressure. For them, these visuals aren't just tools, they're bridges, turning abstract mathematics into narratives even non-scientists can feel. When LIGO first detection matched a decade-old simulation frame for frame, it wasn't just validation, it was a moment of shared awe, proof that even in the darkest corners of the universe, humanity's imagination can light the way. What's next? As supercomputers grow faster, simulations will dive deeper into the merger's chaotic core, probing quantum gravity's shadowy realm. Some teams are already training AI to predict collisions in seconds instead of months, while others are crafting virtual reality experiences that let researchers step inside a black hole's warped spacetime. The goal isn't just accuracy, it's immersion, making the unseeable not just calculable but visceral. Because in the end, these simulations remind us of something profound. The universe's most violent events aren't just equations on a chalkboard. They're stories written in spacetime, waiting to be decoded one line of code at a time. Behind every whisper of spacetime captured by LIGO detectors lies an untold story of human perseverance, a global tapestry of scientists, engineers, and dreamers who spent decades chasing ripples many thought impossible to catch. Take Rainer Weiss, the MIT physicist who first sketched the laser interferometer design on a chalkboard in the 1970s, battling skepticism from peers who called it Weiss's crazy toy. Or Kip Thorne, the theoretical visionary who bet a bottle of fine wine that gravitational waves would be found by 2010, a wager he lost but only by 5 years. Then there's the quiet heroism of people like Ronald Drever, the Scottish instrument builder whose tinkering in a Caltech basement solved critical noise problems, or the army of graduate students who spent nights debugging glitches caused by everything from desert winds to fluorescent lights flickering in the lab. The breakthrough wasn't just about brilliance, it was about stubbornness. Early prototypes failed spectacularly. Bars of aluminum designed to ring like bells when waves passed stayed stubbornly silent. Funding dried up repeatedly, with one government review famously declaring the project not worth a dime. Yet the team kept iterating, replacing steel wires with delicate glass fibers, inventing seismic isolation systems so sensitive they could cancel out footsteps in the hallway, even developing mirror coatings so flawless they scattered less than 1 photon in a million. By the time LIGO upgraded, advanced detectors went online in 2015, the machines could measure displacements 10,000 times smaller than an atomic nucleus, a precision equivalent to measuring the distance to Alpha Centauri down to the width of a human hair. What's often overlooked is how deeply international this effort became. The LIGO scientific collaboration grew to over 1,000 members from 20 countries, with contributions ranging from Japanese cryogenic technology to German supercomputers crunching data. When Virgo, the European detector near Pisa, joined the network in 2017, its slightly different orientation helped triangulate sources with pinpoint accuracy. Meanwhile, India's upcoming LIGO India promises to expand coverage further, while Japan's underground Kagra detector, shielded from thermal noise by frigid temperatures, adds yet another ear to the cosmic listening post. This wasn't just science, it was diplomacy, with researchers sharing algorithms, calibrating clocks across continents, even delaying announcements to ensure colleagues in distant time zones could participate in discoveries. The cultural ripple effects have been just as profound. That first detection in 2015 didn't just make headlines, it inspired art installations, symphony compositions, even a Pulitzer Prize-winning New Yorker article. School children now build miniature interferometers from LIGO, while documentaries bring black hole collisions to IMAX screens. Perhaps most telling is how gravitational waves have reshaped our collective imagination. Those chirps translated into sound aren't just data, they've become cultural artifacts played at TED Talks and embedded in smartphone apps, letting anyone hear the universe's hidden rhythms. At its heart, this story reminds us that monumental discoveries rarely belong to lone geniuses. They're built by communities, by the technician who noticed a suspicious cable vibration, the programmer who wrote code to filter out earthquakes, the theorist who spent 30 years refining merger models. When LIGO team finally held their historic press conference, they didn't just announce a detection, they proved that patience, collaboration, and sheer grit could unlock nature's best-kept secrets. And as new detectors come online, they're not just expanding our view of the cosmos, they're honoring every unsung hero who helped turn Einstein's ghostly waves into a language we can all understand. Gravitational waves have transcended the realm of astrophysics to become a cultural phenomenon, weaving their way into movies, music, and even visual art with a magnetism that's hard to ignore. Take Christopher Nolan's Interstellar, where the black hole gargantua wasn't just a CGI spectacle, it was a scientific marvel. Physicist Kip Thorne worked closely with the effects team, using Einstein's equations to render the black hole's accretion disk and gravitational lensing with unprecedented accuracy. The result, a swirling, radiant halo that bent light exactly as relativity predicts, mesmerizing audiences while sneakily educating them. But it's not just Hollywood blockbusters. Indie films like The Theory of Everything dramatized the human quest behind gravitational wave detection, turning equations into emotional narratives. Music has embraced these cosmic ripples too. Composer Hans Zimmer collaborated with Thorne to sonify black hole simulations for Interstellar's score, translating space-time distortions into eerie, pulsing chords. Meanwhile, experimental artists have turned LIGO real gravitational wave data into ambient soundscapes, stretching those faint chirps into haunting melodies that tour concert halls. Even pop culture isn't immune. When LIGO announced its first detection, The Late Show recreated the event with symbols and a their min, proving science could be as entertaining as it is profound. Visual artists, too, have latched onto the metaphor of spacetime as a fabric. Installations like Gravitational Waves by Rafael Lozano Hema use suspended pendulums to mimic colliding black holes, letting visitors physically interact with the invisible forces shaping our universe. Museums now feature immersive exhibits where projections warp and ripple underfoot, simulating the passage of a gravitational wave. These creations aren't just pretty, they're pedagogical, bridging the gap between abstract theory and visceral experience. Why does this resonate so deeply? There's something primal about the idea of hearing the universe. Gravitational waves turn cosmic violence into something intimate, a whisper from the void that feels almost personal. They democratize astrophysics, offering a tangible hook for curiosity. A child might not grasp space-time curvature, but the notion that black holes sing when they collide. That sticks. This cultural ripple effect has real educational power. When Interstellar hit theaters, searches for wormholes and relativity spiked. LIGO discoveries have inspired STEM outreach programs, with students building mini interferometers from scratch. Science communicators leverage these pop culture touchpoints to explain complex ideas, comparing neutron star collisions to kilonovas in superhero movies. or using Doctor Who's timey-wimey plots to discuss space-time distortion. The lesson is clear: when science and storytelling collide, they don't just entertain, they illuminate, turning distant cosmic phenomena into stories we feel in our bones. And as gravitational wave astronomy advances, its cultural footprint will only grow, reminding us that the universe's greatest mysteries are also its most compelling narratives. Gravitational waves aren't just transforming astrophysics, they're revolutionizing how we teach the cosmos. Imagine a high school physics class where students don't just read about Einstein's theories but hear them, listening to the actual chirp of colliding black holes captured by LIGO. These cosmic vibrations have become a gateway, turning abstract concepts like space-time curvature into something visceral and immediate. Educators are seizing this moment, using gravitational waves as a living textbook, one where the universe's most violent events become teachable moments. Take the Black Hole Hunter program, where students analyze real LIGO data to identify gravitational wave signals, or the Einstein's Messengers project, which lets classrooms simulate merging neutron stars on classroom laptops. Suddenly, relativity isn't just equations on a chalkboard, it's a soundtrack from the edge of reality. Universities are racing to adapt too. MIT now offers a course where students build miniature interferometers from laser pointers and mirrors, while Stanford's Gravity Spy initiative enlists undergrads to classify glitches in LIGO data, turning noise filtering into a citizen science game. The ripple effects extend beyond STEM. Art students sketch visualizations of warped space-time, philosophy classes debate whether gravitational waves exist independently of our detectors, and music majors compose symphonies inspired by the frequencies of cosmic collisions. This interdisciplinary wave reflects a deeper truth. Gravitational waves aren't just a scientific tool, they're a cultural catalyst, blurring lines between subjects and sparking creativity in unexpected places. Public outreach has become just as innovative. Science museums like the Exploratorium in San Francisco let visitors feel gravitational waves by walking on suspended floors that mimic space-time ripples, while planetariums project immersive shows where audiences watch black holes collide overhead. The National Science Foundation's LIGO Little Listeners program even tailors activities for preschoolers, using slinkies and jump ropes to demonstrate wave propagation. These efforts aren't just about education, they're about equity. By making cutting-edge research accessible, institutions are dismantling barriers, inviting communities traditionally excluded from astrophysics to participate in humanity's greatest detective story. Yet with this power comes responsibility. Gravitational wave astronomy raises ethical questions rarely discussed in classrooms. Who owns the data from these collisions? The scientists who collected it, the public who funded it, or the universe itself? How do we balance the carbon footprint of supercomputers modeling black holes against the urgency of discovery? And as detectors grow more sensitive, could they someday eavesdrop on gravitational whispers from intelligent life? These aren't hypotheticals, they're conversations already happening in ethics seminars and policymaking circles, proving that science doesn't exist in a vacuum. The most profound lesson gravitational waves offer might be this: discovery is a collective endeavor. From the grad student spotting a signal in noisy data to the teacher inspiring a future Nobel laureate, each person plays a part in decoding the cosmos. And as the next generation learns to listen to space-time's subtlest murmurs, they're not just studying science, they're joining a conversation that spans the ages, one where every chirp and ripple is an invitation to wonder. Every great leap in understanding the cosmos comes with a question. Just because we can explore, does that mean we should? The pursuit of gravitational waves isn't just a scientific endeavor, it's a philosophical crossroads. Projects like LIGO cost hundreds of millions of dollars, demanding resources that could fund hospitals, schools, or climate initiatives. Critics argue that in a world grappling with inequality and ecological crises, pouring vast sums into detecting invisible space-time ripples might seem indulgent. Yet supporters counter that the price tag is a fraction of global military spending, and the returns are immeasurable. Beyond black holes and neutron stars, these discoveries ignite curiosity, inspire generations of scientists, and remind us that humanity's potential stretches far beyond Earth's boundaries. The debate isn't just about money, it's about priorities. Building LIGO required mining rare metals, consuming energy, and displacing local ecosystems for its far-flung facilities. Some ask whether the environmental footprint of big science undermines its noble goals, but others point to the unintended benefits. The lasers developed for LIGO now refine medical imaging, while its vibration-dampening tech protects sensitive labs worldwide. Scientific frontiers often spin off innovations that ripple into daily life. From GPS to cancer treatments, proof that cosmic curiosity and earthly progress aren't mutually exclusive. What's often overlooked is how these projects transcend borders. Gravitational wave astronomy is one of the few fields where data is shared globally in real time, with researchers from rival nations collaborating as if politics didn't exist. When LIGO detected its first black hole merger, the paper's author list spanned 18 countries, a testament to shared purpose. In an era of division, these discoveries offer something rare, a unifying narrative. A farmer in Kenya and a student in Norway can both marvel at the same cosmic collision, a reminder that we're all under the same sky. For the scientists behind these breakthroughs, the weight of responsibility is personal. Many speak of sleepless nights not just from debugging detectors, but from wrestling with the scale of their work. One researcher described holding her newborn while reviewing neutron star data, struck by the paradox of studying violent cosmic births as a child slept peacefully. Another recalled his grandfather, a refugee who never finished school, weeping when he learned his grandson helped prove Einstein right. These aren't just careers, they're human stories, intertwining ambition with humility. The ethical calculus of cosmic exploration has no easy answers, but perhaps the most compelling argument lies in what we risk by not looking up. History shows that societies that stop investing in fundamental questions eventually stagnate, losing the spark that drives innovation. Gravitational waves remind us that science isn't just about utility, it's about wonder. And in a world that often feels fractured, that shared wonder might be the most valuable discovery of all. The moment that gravitational waves first appeared on LIGO screens, the room didn't erupt in cheers, it fell into stunned silence. We'd spent decades preparing for this, recalls physicist Nergis Mavalvala. But when the signal actually came through, it was like time stopped. That chirp wasn't just data, it was a voice from 1.3 billion years ago speaking directly to us. For many scientists, the emotional impact was overwhelming. Gabriela Gonzalez, former spokesperson for the LIGO collaboration, describes trembling as she verified the signal. "I kept thinking, this ripple passed through dinosaurs, through ancient civilizations, through wars and revolutions, all to reach us now. We're so small, and yet here we are, catching echoes from the dawn of time." What's striking isn't just the scale of the discovery, but the raw humanity behind it. Kip Thorne, whose theoretical work laid the foundation for LIGO, admits he wept when hearing the black hole merger's sound for the first time. It wasn't just confirmation of Einstein's equations. It was proof that the universe is alive with motion, that space itself can tremble like the skin of a drum. Younger researchers echo this sense of awe. Laser scientist Sheila Dwyer recalls her first night shift monitoring the detector. I'd stare at the Milky Way through the observatory doors, realizing the machine I was babysitting could hear things those stars couldn't even see. This work has a way of humbling even the most seasoned minds. Astronomer Jocelyn Bell Burnell, who discovered pulsars, reflects on how gravitational waves redefine our place in the cosmos. We used to think we were observers, separate from the universe. Now we know we're immersed in it, bathed in ripples from events older than life itself. For some, like cosmologist Carlos Lausto, the discoveries blur the line between science and spirituality. When you model two black holes colliding, you're touching something primordial, a moment where time and space lose meaning. It's impossible not to feel like you're glimpsing the machinery of creation. The emotional resonance extends beyond labs and lecture halls. When LIGO teams shared their findings with indigenous communities, Navajo elders recognized the parallels to their oral traditions, stories of the cosmos as a woven fabric, vibrating with energy. Meanwhile, poets and philosophers grapple with the implications. As one researcher mused, if space-time can stretch like taffy, what does that say about the nature of reality? Are we just patterns in the waves, temporary eddies in a flowing river of gravity? Perhaps the most profound reaction came from Ry Weiss himself, now in his 90s, reflecting on a lifetime of chasing ghosts. We built this machine to listen to the universe. But sometimes when the detectors are quiet, I wonder if it's the universe listening back. In the end, gravitational waves don't just reveal black holes, they reveal us, fragile, persistent, and endlessly curious, straining to hear the music of the spheres with machines finer than spider silk and hearts wide open to wonder. Gravitational waves don't just reveal black holes, they reveal something far more profound about ourselves. That faint chirp you hear from colliding black holes. It traveled over 1 billion years to reach us. When those waves began their journey, Earth was a lifeless rock, and multicellular organisms wouldn't exist for another 800 million years. The sheer scale of time and distance involved makes our human concerns feel microscopic, yet here we are, building machines delicate enough to catch these ancient whispers. It's a cosmic paradox. The smaller we feel in the universe, the more remarkable our ability to understand it becomes. This shift in perspective isn't new. When Copernicus displaced Earth from the center of the universe, it wasn't just astronomy that changed, it was our entire sense of place. Galileo's telescope showed moons orbiting Jupiter, proving not everything revolved around us. Hubble revealed galaxies beyond our own, turning the Milky Way into just another speck in an ocean of stars. Now, gravitational waves deliver the latest humbling truth. We're not just physically small, but temporally insignificant. The collisions we detect happened before animals crawled onto land, before continents took their current shapes, before humans even existed. And yet, these events are only now reaching us like letters mailed across the eons. What does it mean to hear the cosmos? Unlike our ancestors who mapped the heavens with naked eyes, we're no longer passive observers. These waves let us touch the universe directly, feeling its vibrations as intimately as a drumscan feels a beat. There's poetry in that, the most violent events in existence speaking to us through the subtlest tremors. A supermassive black hole merger might shake space-time with the power of 100 quintillion suns, yet by the time it reaches Earth, the distortion is smaller than an atomic nucleus. To detect that requires not just technology, but imagination, the audacity to believe we can perceive what our senses were never built to notice. Yet this humility comes with unexpected power. The same waves that dwarf human existence also give us tools to shape our future. Precision timing from pulsar wave studies could revolutionize GPS. Gravitational wave detectors inspire earthquake early warning systems. Even the laser technology developed for LIGO now detects cancers earlier by spotting microscopic tissue changes. The universe's grandest phenomena are whispering secrets we can turn into earthly breakthroughs. Perhaps that's the ultimate lesson. In the cosmic scale, we're both insignificant and extraordinary. A species that evolved on a random rock, yet somehow learned to decode the universe's hidden language. Every chirp from a black hole collision isn't just data. It's an invitation to keep listening, to keep reaching, even as we embrace our fleeting place in the grand symphony of space-time. The hunt for gravitational waves didn't just revolutionize astronomy, it sparked a quiet revolution in technology, spinning off innovations that now touch everything from medical labs to construction sites. Take the lasers at LIGO Heart. To measure space-time ripples smaller than a proton, scientists had to create the purest, most stable laser beams ever made. These aren't your average supermarket barcode scanners. They're so precise they can detect a mirror moving less than 1,000th the width of a single atom, a level of sensitivity that's now being adapted for early cancer detection. Researchers are using similar laser systems to spot microscopic tissue changes long before tumors become visible on traditional scans, turning a tool built for cosmic exploration into a potential lifesaver. Then there's the challenge of vibration isolation. To hear the universe's whispers, LIGO had to silence Earth's constant noise, passing trucks, distant earthquakes, even the rumble of ocean waves. The solution, a suspension system so advanced it could cancel out vibrations like noise-canceling headphones for an entire building. Today, versions of this tech protect electron microscopes in labs, stabilize precision manufacturing robots, and even help architects design skyscrapers that withstand earthquakes. What began as a way to steady mirrors for astrophysics now keeps sensitive equipment steady in hospitals and factories worldwide. This ripple effect isn't unique. History's most ambitious science projects often birth unexpected tools. NASA's quest for space-age materials gave us memory foam mattresses. Particle accelerators designed to smash atoms led to breakthroughs in radiotherapy for cancer. Like those missions, gravitational wave research proves a powerful truth. When we push technology to its limits to answer fundamental questions, the benefits rarely stay confined to a lab. The very act of trying to listen to black holes forced engineers to invent better sensors, quieter materials, and smarter algorithms, each with spin-offs we're only beginning to explore. But the real value goes beyond gadgets. These innovations underscore why curiosity-driven science matters. When Rai Weiss first sketched his interferometer design in the 1970s, no one was thinking about medical lasers or earthquake-proof buildings. They were chasing a ghostly prediction from Einstein's equations. Yet decades later, that pure pursuit of knowledge has yielded tools that reshape daily life. It's a pattern as old as science itself. The questions that seem most abstract today often become the foundations of tomorrow's breakthroughs. Now, as gravitational wave astronomy enters its next chapter, with space-based detectors and quantum-enhanced sensors on the horizon, the technological frontier is expanding again. Future interferometers might borrow quantum entanglement tricks from computing to boost sensitivity, techniques that could revolutionize encryption or materials science. The same supercomputers modeling black hole mergers are now training AI to predict extreme weather or design new drugs. Even LIGO data analysis methods, honed to pick cosmic signals from noise, are helping seismologists spot hidden earthquake precursors. The lesson: when we build machines to listen to the universe often whispers back in ways we never anticipated. And as the next generation of detectors takes shape, one thing is certain: the greatest spin-offs may still be waiting in the static, ready to surprise us all. Every ripple in space-time captured by LIGO detectors comes buried in an ocean of noise, thousands of gigabytes of data pouring in every day, filled with false alarms from earthquakes, passing trucks, even the vibrations of trees swaying in the wind. Finding a genuine gravitational wave in this deluge is like trying to hear a whisper in a hurricane. The numbers are staggering. A single detector run can produce petabytes of raw data, enough to fill 1 million DVDs. Traditional analysis methods would take months to scan this information, but gravitational waves wait for no one. Their signals fade into the background unless caught in real time. This is where the marriage of astrophysics and artificial intelligence becomes revolutionary. Machine learning algorithms, trained on millions of simulated black hole and neutron star collisions, now scan LIGO data streams like cosmic bloodhounds. They don't just look for patterns, they learn them, adapting to spot the subtle fingerprints of gravitational waves hidden in the static. Some of these AI systems are so sensitive they've flagged signals human analysts initially dismissed as glitches, later confirmed as real events. The most advanced models can even predict what kind of cosmic crash produced a wave, estimating the masses of colliding black holes or the spin of neutron stars before scientists finish their coffee. Yet for all their power, these algorithms aren't replacing human intuition, they're amplifying it. Take the case of GW190521, a gravitational wave that defied expectations. When AI first flagged it, the signal didn't match any known template. Was it a glitch, a new type of collision? Human researchers stepped in, comparing the anomaly to exotic theories like boson star mergers or primordial black holes. This dance between machine efficiency and human creativity is reshaping discovery. AI handles the brute force searching, while scientists focus on the tantalizing outliers that could rewrite textbooks. The next frontier is even more ambitious: real-time multi-messenger alerts. When LIGO detects a potential wave, AI now races to triangulate its origin within minutes, automatically notifying telescopes worldwide to swing toward the source. During one neutron star collision in 2017, this system worked so swiftly that optical telescopes captured the kilonova's afterglow within hours, a feat that would have taken weeks with manual analysis. But challenges remain. As detectors grow more sensitive, the data tsunami will swell, forcing scientists to develop quantum computing techniques and neuromorphic chips that mimic the human brain's efficiency. What keeps researchers awake at night isn't just processing today's data, it's preparing for tomorrow's. Future observatories like the Einstein telescope will generate exabytes of information, demanding AI that can learn on the fly, distinguishing between cosmic signals and entirely new categories of noise. Some teams are already experimenting with algorithms that flag unknown unknowns, patterns that don't match any existing model, hinting at phenomena we haven't even imagined yet. This flood of data isn't just a technical hurdle, it's a philosophical shift. For centuries, astronomy relied on sparse, precious observations. Now we're drowning in riches, scrambling to drink from a fire hose of cosmic information. The answers to some of astrophysics' biggest questions, dark matter's nature, quantum gravity's secrets, might already be hiding in the static, waiting for the right algorithm or human insight to tease them out. And as the machines grow smarter and the detectors more sensitive, one thing becomes clear: the universe's whispers are turning into a roar, and we're just learning how to listen. For all their revelations, gravitational waves have left us with cosmic puzzles even more baffling than the ones they've solved. Take dark energy, the mysterious force accelerating the universe's expansion. Gravitational waves from distant neutron star collisions could act as cosmic yardsticks, measuring how fast space itself is stretching over time. but current detectors aren't sensitive enough to catch these faint, low-frequency ripples yet. Future observatories like LISA, floating millions of miles apart in space, might finally trace dark energy's fingerprints by comparing how gravitational waves from ancient collisions arrive compared to their visible counterparts. Then there's the elephant in the room, quantum gravity. Einstein's equations break down at the singularity inside black holes, where space-time curvature becomes infinite. Some theories suggest that if we could detect gravitational waves from the very instant of a black hole merger, a Planck-second snapshot of that chaotic collision, we might spot subtle deviations from relativity, hints of quantum effects warping space-time itself. It's like trying to hear the individual notes in a thunderclap, but next-generation detectors with quantum-enhanced sensitivity could get us close. Other enigmas lurk in the static. Why do some black holes pair up so easily while others roam solo? Are there primordial black holes forged in the Big Bang's first moments, hiding in LIGO data? And what about dark matter? Could certain exotic particles create faint gravitational murmurs as they clump together? The absence of answers isn't failure, it's a map of where to point our cosmic microphones next. The most thrilling possibility: gravitational waves might reveal something entirely unimagined. Before LIGO first detection, theorists didn't predict the abundance of heavyweight black hole binaries we've found. Future surprises could rewrite physics, evidence of extra dimensions in distorted waveforms, hints of wormholes bridging distant points in spacetime, or even, dare we dream, signals from intelligent civilizations manipulating gravity itself. This is the essence of exploration, not just answering questions, but discovering better ones. Every time we improve our detectors, we're tuning into channels the universe didn't know it had. The static between known signals isn't empty noise. It's the static of possibility, crackling with whispers of truths we've only begun to grasp. And that's why the hunt continues, because the greatest discoveries aren't the ones we plan for, but the ones that catch us by surprise, reminding us that the cosmos always has another secret up its sleeve. Imagine if we'd given up on radio astronomy in the 1930s, dismissing those faint hisses from space as mere static. We'd have missed pulsars, quasars, the cosmic microwave background, the very foundations of modern cosmology. Gravitational wave astronomy stands at a similar threshold today. Those faint chirps from colliding black holes, they're just the first words in a language we're only beginning to decipher. The detectors we've built are like the earliest crystal radios, crude compared to what's coming, but revolutionary in what they've already revealed. Consider what's at stake. Right now, gravitational waves are our only direct line to the universe's darkest secrets. Black holes, which emit no light, can't hide from these ripples in spacetime. Neither can neutron stars, cosmic strings, or the hypothetical echoes of the Big Bang itself. Traditional astronomy is like watching a silent movie. Gravitational waves add the soundtrack, revealing plot twists we never saw coming. Already, they've exposed black holes of impossible sizes, neutron stars with crushing densities, and mergers in cosmic backwaters we'd never thought to look. And just as radio telescopes unexpectedly discovered phenomena like pulsars, gravitational wave detectors could stumble upon entirely new classes of objects, things we haven't even dreamed up yet. The investment isn't just about satisfying curiosity, it's about rewriting the rules. Every time we've opened a new window on the cosmos, we've been blindsided by discoveries. X-ray astronomy unveiled black holes devouring stars. Infrared telescopes exposed stellar nurseries hidden in dust. Gravitational waves could unmask the universe's most elusive players, primordial black holes from the dawn of time, or even cracks in Einstein's theory of relativity. Somewhere in that static might lie clues to quantum gravity, dark matter, or dimensions beyond our perception. But the real payoff isn't just in the stars, it's here on Earth. The technology born from this quest already spins off into medicine, computing, and materials science. The lasers, vibration dampeners, and AI algorithms honed by LIGO are solving problems no one anticipated when the project began. History shows that fundamental research, the kind driven by pure wonder, often yields the most practical breakthroughs. GPS, MRI machines, and the internet itself all sprang from scientists chasing abstract questions, not profit margins. Supporting this field isn't just about funding machines, it's about nurturing a mindset. In an era of short-term thinking, gravitational wave astronomy reminds us that some truths take decades to uncover, and that patience is the companion of profundity. The next generation of detectors, like LISA and the Einstein telescope, won't just be more sensitive, they'll be explorers in uncharted territory, mapping a universe we've only glimpsed in fragments. This is how science moves forward, not in leaps but in whispers, each one urging us to listen closer. The static of the cosmos isn't empty noise, it's the sound of the unknown, waiting for someone bold enough to tune in. And if history's any guide, the greatest discoveries aren't the ones we're hunting for, but the ones that surprise us when we're paying attention. From a scribbled equation in Einstein's notebook to the faint chirp echoing through LIGO detectors, the story of gravitational waves is one of human imagination colliding with cosmic reality. It began as a ghostly ripple in the fabric of mathematical theory, a prediction so fragile that even its creator doubted we'd ever catch it in the wild. Yet here we are, a century later, with machines so precise they can measure distortions smaller than an atom, tuning in to collisions that shake the universe. Each detection is a time capsule, carrying news from epochs before Earth formed, from places light could never reach. These silent signals have done more than confirm a theory. They've handed us a new lens to see the invisible, turning black holes from mathematical myths into tangible actors in the cosmic drama. What's truly astonishing isn't just the science, but what it reveals about our place in the cosmos. Those ripples connect us to events of unimaginable violence, black holes merging at half the speed of light, neutron stars tearing each other apart in sprays of gold and platinum. Yet by the time their whispers reach us, they're gentler than a breeze, felt only by machines crafted over decades of stubborn ingenuity. There's poetry in that contrast, the universe's loudest crashes arriving as the softest tremors, bridging the gap between the cosmic and the intimate. This journey has rewritten the rules of astronomy, but its deeper gift is perspective. Every chirp from a distant collision reminds us that space isn't empty, it's a living, breathing thing, vibrating with stories we're only beginning to hear. It's humbling to realize that while we've mapped the stars for millennia, we've only just learned to listen to the spaces between them, and the symphony is far from over. With every upgrade to our detectors, every new observatory joining the global network, we're tuning into frequencies that might reveal dark matter's dance, the birth cries of time itself, or phenomena we haven't even named yet. So tonight, when you look up at the stars, remember this: the sky isn't silent. Those points of light are just the visible notes in a far grander composition, one played on the strings of space-time in a key we've only just begun to decipher. The universe has been speaking all along in a language of ripples and whispers. Now, thanks to the curious minds who refuse to stop listening, we've finally learned how to lean in and hear it. And that's the real wonder, not just that the cosmos talks, but that we've grown clever enough to understand.